Okay, so first of all, welcome everybody. Good morning, good evening, good afternoon. My name is Marcello. I come from ICTP, and I'm really happy to contribute to this Quantum Africa 6th edition organized by Franco and Omu. And the story I will tell you today is a kind of a continuation from a very different perspective of what Terry Rudolph told you at the beginning. And it's a story about how can we understand how to build better quantum memories, which have some sort of topological protection. And Terry already mentioned the toric code, and I will go into detail into that. But before starting the talk, I would like to acknowledge the people who actually did most, if not all, of the work. Riccardo Andreoni, Adriano Angelone, Federica Surace, and Poetry Tarabunga. And so the results are available at this preprint if you are interested in more details. So the big picture is the following. So if we want to build a quantum simulator of a quantum computer, what are the ingredients that we need? Well, to some degree of approximation, what we need is a set of qubits that interact and then we can manipulate properly. There is always, however, kind of ubiquitous issue is that we cannot have perfectly isolated degrees of quantum degrees of freedom. There is always some degree of coupling to an environment, okay, which is typically large. And in this simplified picture is denoted by an energy scale, or which is gamma, okay? The decay rate, what we will call decay rate of the qubit. The key challenge in quantum simulation and computing is to have information in our qubits stored in a reliable manner. This is really a key thing. And from those of you that come more from a quantum optics perspective, we know that this is not possible, okay? Or at least there are fundamental impediments to this. And the typical example, textbook example of that is Wigner-Weisskopf theory of spontaneous decay of an atom coupled to an electromagnetic field. Okay? So this is very much the same motivation or part of the same motivation of Terry's talk this morning. Okay? Now, oops, there is a problem here. So the key element or the key model that distill some of the fundamental ideas that have been developed towards realizing a robust quantum memory is the toric code. Apologize for the slides. So the toric code is just a two-dimensional spin system where we define on the bonds of a square lattice, where you see these gray boxes, spins 1/2. And then we put interactions between these spins 1/2, which are of two types. The first type is this B-plaquette. This B-plaquette is actually involving only spins belonging to the same plaquette. For instance, this 4 spin I'm indicating now with my pointer. And it's a product of sigma X operations. And then there is another part of the Hamiltonian, which instead of acting on the plaquettes, acts on the vertices. And this is an example, what I call this A+. And instead of being a product of sigma X around each vertex, which will make the model classical, it's a product about sigma Z. Okay? Now, this toric code has been proposed by Kitaev in the late 90s. And some of its key features are that it can store in a reliable manner, which we call robust, 2 qubits in a non-local manner. Okay? And I would like to skip on the details. This, I think, is extremely important. And another feature which is extremely important is that it allows, under certain caveats, to have reliable schemes for error correction. The origin of it, if we look at it beyond, from a different angle than the quantum information, is that this toric code realizes what in condensed matter is called a spill liquid, which is a deconfined phase of a gauge theory. Now, forget about all these words. If you have never heard of them in this present context, I will try to introduce them step by step later on. But I would like to point out that there is a very different angle that one can take to understand this topological manner. So what is, this toric code model is extremely elegant. It can be solved analytically, and a lot of its features are actually important also for other kind of problems in physics. There is, however, one key issue is that it's very hard to realize its Hamiltonian dynamics. Okay? And there are several reasons why it's hard, and the most basic one is that realizing naturally 4-body interactions is something which we don't necessarily know how to do as well as 1 or 2-body interactions. Now, jump step from late 90s to 2021, there was an experiment last year performed in the group of Misha Lukin at Harvard. And this experiment consisted in an array of Rydberg atoms, coupled via laser to Rydberg states. And the effective dynamics was not the one described by the toric code, was some sort of easy model on an exotic lattice. And this exotic lattice is portrayed on this picture here on the right. It's a lattice where the atoms are put on the bonds of a Kagome lattice. This lattice is called Ruby lattice. Okay? And via Rydberg interaction, they generate some sort of non-trivial Leysin dynamics that was discussed in an earlier, very interesting numerical study to show the same type of physics that one has in the toric code. And this was indeed what was observed indirectly by Misha and his group. And in particular, what they focus at are what in quantum information are called syndromes, and what in energy physics are called loop operators, or kind of Wilson loop operators, even though there are important differences I will mention later on. And in particular, what we were able to show is that for specific values of the laser parameters that their system had, the Rabi frequency and the detuning, the specific details are not important at the moment. It was possible to stabilize a phase which has exactly the same properties of the toric code. Okay? This, I think, is extremely remarkable because it's one of the first demonstrations at the microscopic level of toric code dynamics in a system that can be controlled and which is not microscopic, but it's made out of hundreds of degrees of freedom. I think in this specific case, they have around 200 atoms in the system. Now, the key question I want to tell you, that I want to address in this talk is the following. What is the origin of such very potentially useful quantum memories that we call Rydberg spin liquids? So why do they appear in this type of physical systems? Okay. So, and the motivations for us to ask these three questions are the following. First of all, if we understand why this phase is actually present in these experiments, maybe we can design further optimized experiments where the properties of this quantum memory are even more robust. Okay, so we need, but this implies that we know why it is there. The second reason why we want to address this question is that maybe we are not just ending up in working with a lucky model. There is a new class of quantum mechanical system that can have these very nice properties, and this can open up possibilities for new theoretical as well as experimental developments. And third reason is that understanding the origin of this phase can also give us a better handle on how to diagnose this phase. And this is not as simple model as the toric code, so we want to have very stable and reliable diagnostics. And the result that I will summarize in the following is that actually there is a new class of exactly soluble models that does have a description, which we call, in condensed matter typical, called dual description, which is exactly the same one of the toric code. And what is remarkable is that instead of having four-body interactions, all these models are just made of two-body interactions, which are, in some sense, much more natural to be realized. I will discuss some of this. I will not discuss how this can be realized concretely. I mean, this is a bit too long for today. But I also would like to point out that understanding this origin also somehow raises a word of caution on the interpretation of these loop operators that I mentioned you before. So the outline that I propose is the following. I mean, first I will tell you why is the challenge, and actually the challenge is a history of a failure, and I think it's interesting I mean, a failure that I was also involved in. So, and I think it's interesting because it gives us feeling of how difficult it is to actually understand the relation between potential experimental realization and historical dynamics. And in particular, I will tell you about older works in Rydberg gauge theories. And then I will tell you instead the set of new results. Okay? Now, we need a bit of a prequel because I've used this word gauge theory several times, and this is not, I mean, this is a wording that is not necessarily the one that is utilized in either in quantum information or in condensed matter, is something which we typically think it's closer in spirit to energy. So I will take a few minutes to try to give you an introduction to this based on simple statistical mechanics models. And the statistical mechanics model I will tell you is about ice. Okay, so how people have modeled ice. This is an history that goes back to the late 30s and early 40s. So ice, we can imagine, we have microscopic degrees of freedom, H2O, and these are essentially modeled by an oxygen atom and 2 hydrogen are close by, and there are small dipoles along both directions. So the electron has to be closer to the oxygen in a very specific manner. And later, and other people in the 30s and 40s, then they model it by just putting this on a square lattice and fixing the position, which is, we know, it's not necessarily the best way of modeling because the structure of ice is not square. Okay, but just to understand what is the basic ingredients, and then they say, okay, let us put the oxygen atoms at the vertices of the lattice, and then we start putting the hydrogen atoms close by. And we know, due to the structure of these molecules, that maximum 2 hydrogen atoms can be next to each oxygen. And we start filling the lattice like this, and we notice immediately that there is a simple rule, okay? That essentially the only states that are allowed in this simple configuration are the one with 2 hydrogens close by. But now what I can do, I can replace, I mean, this very simple model actually is able to predict properties of ice down to percent level, which is quite remarkable, I have to say. It's 2-dimensional from geometry. But it tells you that this thing about arranging hydrogen is the correct way of modeling it. Anyway, I would like to use it to introduce gauge theories. So the way I do it is the following. So instead of utilizing the oxygen, we throw them away because they're not important anymore. And then we decide that we replace the hydrogen with arrows that you can imagine later on they will become spins. And we do it as follows. On a bond where the hydrogen is on the right of the bond, here, we put an arrow pointing on the right. Now, if instead we have the opposite, so the hydrogen on the left of the bond, we put an arrow on the left. For vertical bonds, we do the same. It's kind of rearranging the system, describing it by a set of small local dipoles. Now, if we just apply these rules to the picture on the right, on the left, what we have is that this arrow goes in, this goes down, and so on and so forth. We can replace all of them sequentially. What ends up is that we get configurations like this. Now, configurations like this are not random. They have one very specific feature. If we look at all the vertices, because of this hydrogen rule that we had before, we have always 2 arrows coming in and 2 going out. This is what in statistical mechanics is called ice rule, 2 in, 2 out. Okay? And with this ice rule, what happens is that the configuration space of the statistical mechanics model is not arbitrary, but is only made out of states which can have only 6 types of vertices. These are the only 6 possible ways you can arrange 4 arrows in such a way that 2 are in and 2 are out. In statistical mechanics, this is called 6-vertex model. Now, so far, this was classical. Let us add quantum fluctuation. And now you will recognize immediately why the toric code is a gauge theory. Now, if you want to have dynamics, which is non-trivial, but still satisfies these ice rules, the only thing you can do is try to flip spins. But then you notice that flipping, for instance, one spin is not working. Because if you flip one spin, for instance, this one, what happens is that you have 2 vertices where the ice rule is violated. And the vertices on the upper side, and we have 1 in and 3 out, and here we have 3 in and 1 out. And you will notice that if you do 2 or 3, this is also the same problem. You always have vertices which are wrong. So the minimal interaction that you can write down in this model is something that flips 4 spins. Let me show it to you in this plaquette. On this plaquette, we can flip this spin here, then this other one, then this other one, and then this other one. Well, now that we have flipped the 4 spins, we notice that at each of these vertices, the ice rule is still working because what we have here is 2 in, 2 out, 2 in, 2 out, 2 in, 2 out, and so on and so forth. Okay? So the minimal Hamiltonian for this kind of ice models, which are the prototypical example of gauge theory, is something that contains 4-bond interaction, exactly like in the toric code. The toric code is not S plus S minus, it will be sigma x, sigma x, sigma x, and sigma x. Now, how do we realize in practice these models? Okay, these are not easy because the first thing we have to do is to impose that there is some sort of ice rule. And this is, I mean, typically done as follows. What we take is that we take the sum of the spin components along the, and then we try to engineer a term in the Hamiltonian which just punishes states where this sum is different from 0. This is a very brutal thing. Essentially, we are imposing a constraint on the system energetically. Okay? Because this then will fix the magnetization close to 0, which is equivalent to the 2 in, 2 out, close to each vertex. And then what do? once we have realized that, we have a physical space, what we call physical, which are the space which is resonant, is the state where this ice rule is satisfied. So all the vertices are two up and two down. And then we have some unphysical space separated in energy by something which is of the same order of the prefactor of this interaction, where instead this ice rule is not satisfied. Okay? Then the next thing we will do in an experiment is to introduce some sort of perturbation, which has to be weak. And this perturbation will then induce the dynamics. Okay? For instance, from top to down, by 2 steps, by paying a bit of energy, then you will realize effectively the type of Hamiltonian that you're interested in. Okay? And so this is something that we tried in the past. And it is very complicated because already for the case of spin ice, you need to introduce very different types of interactions. They have to be plateau-like because, for instance, interaction at a given distance a in this model will have to be the same value of as interaction at the distance square root of 2a, which is not so easy. They have to be independent on the orientation because, for instance, if I look at this spin here that I'm pointing out, this has to be strongly interacting with this neighbor along the x direction, but essentially no interacting with on the neighbor on the vertical direction. And then in addition to that, there has to be some sort of angular dependence. Okay? So this is very complicated, and I spare you the details. I mean, the thing that we did, we utilized the Rydberg states. So what are Rydberg states? If you take an atom and you excite it such that its principal quantum number, an alkyl atom, you excite it such a way that its principal quantum number is large, of order of 50 to 100. What happens is that to a first degree of approximation, your atom is essentially a nucleus with positive charge and a single electron at a large distance. So the size of this wave function can span several tens of nanometers. But then what happens is that an interaction like an atom in this configuration is essentially a huge dipole. Okay? And these Rydberg atoms, what they do, they interact through an induced dipole-dipole interaction, so what we call van der Waals interaction, up to distances which are typical in these atomic systems, even a couple of microns. Okay? And these are just few numbers to give you an idea of what the radius of these wave functions is and the typical decay time, the lifetime of these states. Okay? And through a bit of engineering, of understanding how light can shape the interaction, one can realize plateau potential, which are very similar to the one that are needed for this kind of spin ices. Okay? And what we did, we extended that to other models, Kagome, Honeycomb, and so on and so forth. And this was also motivated by, at the very same time, this work was done in 2014 of experiments done at Palaiseau in the group of Antoine Brevet. However, we failed in understanding whether we could realize topological state within these systems. And the detailed reason for that, now I will just mention it, but it's actually something that if you're not familiar with, it will sound obscure. You will have to believe me a bit. The reason is that in order to have this kind of very good, very well protected quantum memories, what you have to realize is a gauge theory of the type that I show you, this quantum ice, on a lattice which is non-bipartite. And it turned out that this is impossible to do with the isotropic interaction which are available in experiments. Okay? There are theories in principle where these states, these very interesting states exist, but to the best of my understanding, it's not possible to realize them with these Rydberg atoms. However, there was these experiments, okay, that I mentioned you before last year, and this followed up. I mean, this was a follow-up of this numerical work, and the key insight of this work is that one does need theories which do not only have this kind of two-in, two-out rule, but they can allow some exceptions. Okay? And these exceptions, in the language that is typically utilized in condensed matter, are called monomer excitations. Okay? Now, these ideas were already around. Actually, in the group of Ernst Zohar, was one of the first to propose this. However, it was not realized that they could have a connection to Rydberg. And within this setting, it might be actually possible to realize these theories. However, it's not clear what the nature of those was. Okay? Because the reason why it was not clear, because if you take naively the simple description of these easy models that one has in these Rydberg experiments, they describe what is called in H theory is so-called U1 quantum link plus X on the Kagome without magnetic fields. And it is known that in the phase diagram of this model, which is indicated here on the right, the regimes that is experimentally realized is this orange regime. This orange regime is a very, very, very strong coupling. And there the system is always ordered. So it can never stabilize a topological phase. So at least from the simple proposed description of U1 quantum link classics, it's not possible. Okay? Now, why is there then this phase? So our approach was actually quite different. So what we wanted to do, we wanted to identify a novel type of degrees of freedom, starting from these lattice models, that map to a solvable model. Okay? Solvable model, what do I mean with that? I mean with a model that we can solve analytically, essentially like the toric code. Okay? And now these two slides, they will be a bit scary. Okay? And I will try to go through them slowly, but of course, feel free to interrupt or to ask questions. And anyway, if some of the details are obscure, I mean, I refer to you to the paper where all of them are spelled out. So what we did, instead of writing down the microscopic Hamiltonian of this Rydberg, we wrote down a much larger Hamiltonian. Okay? And this Hamiltonian is describing R-core bosons of spin 1/2, this is the same, on the Ruby lattice. And we have construction and destruction operator B dagger and B, and density operator N. So this Hamiltonian is made of the following parts. So I will write it like this, is H0 and H1. And both H0 and H1, they contain different types of terms. The first term, you see, is something which is linear in the construction and destruction operator. If you write it down as a spin model, this will just be a sigma X term. Okay? This is the same in both models with different, in both parts of the Hamiltonian with different coefficients. The second term is instead something which is a bit more natural. It's a term which transfers an excitation from one side to the other. It's a hopping. In a condenser matter model, this would be called hopping, tunneling term, only between nearest neighbor. This is also present in both parts of the Hamiltonian. Then what we added is a term that counts the number of bosons at a given site and assign a given energy to that number of bosons in both models, in both parts of the Hamiltonian with different coefficients, W and lambda. And then in addition to those, we add interactions between nearest neighbor, next nearest neighbor, and third nearest neighbor. So the one between nearest neighbor that I call V1 in this simple setting, this we put to infinity. Okay, so you cannot have two atoms on nearest neighbor. And then instead we add interaction V2 and V3, which are nearest neighbor and next nearest neighbor, to be equal exactly to 4W, given number. Okay? Now this is the spin exchange, these are the single spin term, and these are the interactions. Okay? Now, this model is very complicated. However, it turns out that you can map it exactly to the toric code on the Kagome lattice. Okay? And the basic idea is the following, is that the toric code on the Kagome lattice is very, very similar to the one that Terry described in the morning on the square lattice. So it's a model where you have terms which are a vertex, and they are product of sigma z operators. They come with a coefficient W. Then there is one difference with respect to the square lattice. Then on this Kagome lattice, there are two sorts of plaquettes. There are the triangular plaquettes and the hexagonal ones. So, and what do? We put a coefficient which in principle can be different between the triangular plaquettes, J1, and the hexagonal plaquettes, J2. In addition to all of this, we also put terms which somehow compete with the rest of the interaction. And this is one example here, a term that just flips a spin at a given bond, okay? Or a bit of nearest neighbor interaction. This is this third lambda here. Now, this toric code has the advantage that essentially we can interpret it very easily as a gauge theory. So this first term is Gauss law, and the other two terms are kind of different type of magnetic fields. Okay? So this is the connection with the spin ice model I was telling you before in terms of genetic language. Okay. So now how does the mapping works? The mapping is non-trivial, and I would like to explain to you by just looking at the Hilbert space without discussing the Hamiltonian. The Hilbert space, we map it as follows. From the Rydberg side, we have this specific feature that at this triangle, we don't have all possible states because I told you that the nearest neighbor interaction is infinity. So the maximum number of atoms we can put on a triangle is 1. So this implies that we have only 4 states. Either the state with no atom, this one here, or the state with 1 atom, and of the states with 1 atom, we can put 3 because this can be on the upper edge, on the left edge, or on the lower edge of this triangle. Now, what we say is that we map these states to equal weight superpositions of different states in the toric code. The state with no atom, we map to an equal weight superposition of all the spins up or all the spin down. Okay? The state with a defect, with an atom on the upper edge, we map to an equal weight superposition. But now, instead of having all up or down, we have two up or one up. Okay? We essentially flip only the spin on the bond where the Rydberg atom is in this mapping. And then we do the same for the other two states. Okay? This mapping, it's simple, it's one-to-one. And this way we have immediate access to all the possible states in the toric code. Okay? Notice that there are some interesting things that take place. So if we have vertices where, for instance, we have close by odd number of dimers, which are like this one or like this one. This in the gauge theory language. Oh, I see there is something in the Q&A happening. Oh, no, this is not for me. So if there are vertices where there is an odd number of missing, so an odd number of dimers entering, like in this one and this one, these are states where we say there is no charge, okay? Because in principle, you can define what is the so-called background charge in these gauge theories, and then you just adopt this convention. But then the point is that something interesting happens instead if you have an even number of dimers entering in or out, like in this vertex here, or in this vertex here, in this case 0, in the other case is 2. Then we say that in these states, the interpretation is that actually there is a charge, okay, at the given vertex. Okay, I see again something in the QA. So this is the interpretation of this kind of resulting states that we get out of this Hilbert space mapping. Now, are we actually gaining anything out of this mapping? Okay, this you cannot know unless you find out that the resulting Hamiltonian is exactly soluble and it leads to some simple solution that you can analyze and where there is an interesting phase. Now, the mapping of the Hamiltonian is non-trivial, but I point you out a few features. First one is that this mapping works under the following assumption, that there is actually J1, which I remind you is the coefficient of the flipping plaquette terms on the triangular ones, is infinity, and J2 is exactly 0. So we have strong, what are called magnetic field fluctuations, but only on certain type of plaquettes. Now, what is interesting is that for the case of where the small g before is equal to 0, one can prove that under this assumption, the system ground state is actually in the same type of states that is realized in the toric code, which is an equal weight superposition of all possible dynamic state. In condensed matter language, this is what is called a resonating valence bond state. Okay? And this is remarkable because this Hamiltonian is fully local. It's two body interacting, is extremely simple. Still, the original Hamiltonian is like this. Still, you end up in this very highly entangled and non-trivial state. Okay? And now, I mean, so this is the same as in K-type, and I think this is really the first message of my talk, that these blockaded models are dual to gauge theories, which have strong magnetic field fluctuation and which realize very natural toric code dynamics. Now, of course, in reality, there is not this very complicated Hamiltonian with all these terms that I showed you before, fine-tuned to that point. Then the question is this RVB state, is the spin liquid state actually stable against all the perturbations that we expect are there in these experiments? And what we did, we computed the exact overlap with a small system of 36 sites between the exactly soluble point, the exactly soluble wave function, and the system wave function by varying these very different parameters H and G that I did not mention before. And one can see that indeed this phase is not stable to arbitrary perturbation. In this plot is denoted as QSL. So it is stable against finite G until some point, and it is unstable at some point when you increase H. Okay. And this we did by studying fidelity susceptibility and so on and so forth. What was also interesting is that we can in principle study this model also with Monte Carlo, at least in certain regimes. Now what we did, we also tried to understand whether this phase is not stable only against this H and G perturbation, but also against additional perturbation that I flashed over, that were mentioned previously, that are happening in experiments. And we see that indeed, even there is some sort of stability with respect to what happens in experiments. Okay, so there is a sort of very smooth adiabatic continuity between the model that is realized in the experiments, or a very good approximation of that, I should be more precise, and this exact RVB wave function, which justifies that we have found what is the origin and what of this stable quantum, potentially stable quantum memory. We also did something a bit more ambitious, try to characterize what are the properties of this phase. Why are these phases somehow so bizarre in some of their properties? And what we found out is that we have a way of computing the spectrum up to relatively large system, like made out of a few hundred of sites, not in the physical limit, but in a part of the phase diamond, which is adiabatically connected to that. And what we found out is that these models, despite having a very, very small correlation length, which typically we think it's also related to a very large gap, they do not have a large gap. Okay, and this, what you find here on the right, is the energy spectrum of the lowest line 8 states on a torus. There are 4 degenerate ground states manifold, which are the 4 states where the 2 topological qubits should be encoded. But the gap that separates them from the highly excited states, the one that you don't want to populate, is actually small with respect. I mean, this is over 10 to the minus 3 units of the microscopic couplings. Okay? This is very strange. And for those of you that are familiar with field theory, typically, if something like this happens, it implies that underlying Lorentz invariance is very strongly broken. Okay? Okay? So this is weird. Okay? And this also gave us some hint on trying to understand a bit better the type of order parameters that they were discussing in experiments. Now, what they was discussed in the experiment was actually motivated by the earlier theory work. And it's something that is known in energy literature as Fredenhagen-Mark order parameter. Okay? And this is typically, in energy, is done like this. You take 2 particles in your path integral, and then you design a loop in imaginary time, and you close it. This is one observable. And you square this observable, and you divide it by just a conventional loop in imaginary time and space. Okay, this ratio tells you, I mean, the behavior of this ratio as a function of the length of the loop tells you if the theory has topological degree of freedom, at least at the ground state level, or not. Okay, so it's in principle a very interesting diagnostic. However, in the experiment, it's very hard to do this in imaginary time. So what people did, they did it in real space. Okay? Okay. So this is not clear whether we can trust that, because since Lorentz invariance is broken, space and time have very different behavior, at least in principle. Okay? And what we did in the past, actually, before all of this was done, we investigated very similar question in the context of spin ice, exactly the type of Hamiltonian I started at the very early beginning. And what we found out, I mean, this is a study about entanglement, but I want to flash this. This is a study of the Wilson loop, so very similar to the observable that was looked at in the experiment. And we realized that looking at this Wilson loop in real space, which is natural, also in this kind of context we were working at, is actually extremely misleading, because they can give you very unreliable information, okay? Either due to finite size, or even, I mean, and these cylinders were essentially much larger than the numerical simulation I mentioned before, and more or less of the same width of the experiments. And even utilizing certain tricks that people have developed in the context of lattice QCD, it was very unclear whether you can extract anything informative from real space correlation. So this was really a spectacular failure that raises one important caution point, is that when we want to diagnose topological quantum memories away from limits like a toric code where everything is very well understood, one should be really careful in utilizing these syndromes, because they can be misleading. Okay, their behavior can just be related to properties which are not the ones that you're interested in, like topological properties, but for instance, they can be to finite temperature or even finite size effects. Okay? So this is really very important point. So conclusion, I went a bit fast, but I think I'm happy, so there are maybe more time for discussion later on. So what we did, we understood what is the basic mechanism for realizing this robust quantum memories is to combine Rydberg blockade with proper interactions, which are both of transverse field type and XY. There is a message in all of this to energy physics to some extent, is that we can have very nice dual description of Z2 gauge theories, which are made out of two-body interactions, which is very handy. And this description are also good because in principle for experiments, this can be something which is impactful, even beyond the Rydberg atoms. However, our theory also raised certain questions in practice. I mean, this physical interpretation of real space loops is is not clear whether this is actually a good diagnostic. And there is a lot of things that can be done next. I mean, study this model with Monte Carlo, further improve them in terms of quantum engineering, understanding long-range interactions is something not fully clear at the moment, and so on and so forth. And with that, I would like to thank my collaborators again, Adriano, Riccardo, Federico, and Poetry, and thank you for your attention.
Thanks for a great talk, Marcello. Great.
Thank you.
Any questions from the audience there?
Chat. Something is there.
I have many questions, but I can ask you some other day.
I know that this topic is a bit tangent, I mean, not immediately on the line, even though ultimately this is about the stability of these memories, which I find very... Oh, okay, let's see. Hello.
Hi. Hello?
Hello. Hi, I can hear you. Yes, please.
Okay. Thank you for the nice talk. I just want to know more about the concept of spin liquids. I wish to know if you are dealing with half integer spins or just integer spin, and to know if you have also frustrated spin liquids in your systems.
Yes. Okay. The concept of spin liquid is very broad. Okay? In terms of type of models what is a spin liquid? This is it's actually an interesting question, which has a very simple answer, is a deconfined phase of a gauge theory, but the answer then requires several hours to be explained. Okay, so maybe another definition is a state of matter which, even at zero temperature, lacks any type of order. Okay, so a system that does not order. In which type of systems this actually takes place? This is good what you mentioned in your question. I mean, this is mostly frustrated magnets, because frustration is exactly one of the physical mechanisms that prevents system from ordering, because you don't know which interaction wins. Now, related to your question about spin representations and so on and so forth, spin liquids, typically they are studied in the context of half integer spin models, because they are the one where frustration is easier to realize, just easing interactions, they're frustrated. I think there are also studies in the context of integer spin models, and for sure there are spin liquids also there, but on this I know a bit, I don't know much, and I'm not so sure I can tell you anything informative. I'm sorry.
Okay, thank you. Any other questions here? Okay, we don't have any questions again from Kigali. Online, do you have any questions? No, we don't.
No, I don't think so.
Okay. Let's thank Marcello once again.
Thank you. Thank you all.
Thank you very much.
Very nice talk.